The Ordovician mass extinction. You are staring at a computer screen in the Harvard-Smithsonian Center for Astrophysics. The data cascades down in green columns. June 2003, Adrian Malot's gamma-ray burst models fill your monitor. Numbers that should not exist. A stellar explosion, 6,000 light-years from Earth, 445 million years ago. The burst lasted 10 seconds. In those 10 seconds, half of all species on Earth died. You scroll through the extinction rates, 85% of marine species gone. The second largest mass extinction in planetary history. Your coffee grows cold. The mathematics are undeniable. A star exploded in the constellation Sagittarius. Earth's ozone layer vanished in minutes. The biosphere collapsed. This is what cosmic violence looks like when it reaches across galactic distances to touch a blue world orbiting a yellow star. The Ordovician-Silurian extinction event, as documented in the geological record, presents one of paleontology's most enduring puzzles. Between 450 million and 444 million years ago, marine ecosystems that had dominated Earth's oceans for tens of millions of years simply vanished. Trilobites, which had survived multiple previous extinction events, saw their diversity collapse from over 100 families to fewer than 20. Brachiopods, crinoids, and graptolites followed similar trajectories into oblivion. Adrian Malot of the University of Kansas and Brian Thomas of Washburn University published their gamma-ray burst hypothesis in the International Journal of Astrobiology in 2004. Their model suggested that a hypernova explosion within 6,000 light-years of Earth could have produced a gamma-ray flux powerful enough to deplete 50% of the planet's stratospheric ozone layer within seconds. The Hubble Space Telescope has observed such hypernovae in distant galaxies, cataloging events that release more energy in 10 seconds than our Sun will produce over its entire 10 billion year lifespan. Here's what makes this scenario cosmically terrifying. A gamma-ray burst channels the rotational energy of a collapsing massive star into twin jets of electromagnetic radiation traveling at 99.9% the speed of light. When these jets sweep across space, they carry temperatures exceeding 1 trillion Kelvin and magnetic fields trillions of times stronger than Earth's. The Fermi Gamma Ray Space Telescope has detected bursts from galaxies 12 billion light-years away. Their radiation still intense enough to temporarily blind the spacecraft's sensors. The standard cosmological model explains gamma-ray bursts as the birth cries of black holes. When stars exceeding 30 solar masses exhaust their nuclear fuel, core collapse occurs in less than 1 second. The infalling matter rebounds off the incompressible neutron core, driving shock waves outward, while the star's magnetic field channels the explosion's energy into collimated jets. These jets pierce through the stellar envelope, accelerating matter to relativistic speeds and generating the observed gamma-ray signatures. But the Ordovician extinction presents characteristics that traditional explanations struggle to address. The fossil record shows a two-phase extinction pattern: an initial pulse that eliminated deep-water species, followed by a secondary die-off that devastated shallow marine communities. Ice Age conditions persisted for nearly 500,000 years, far longer than typical climate fluctuations would predict. Most puzzling, the extinction disproportionately affected organisms living in open ocean environments, while leaving many coastal and freshwater species relatively unharmed. Some astrophysicists suggest that a nearby gamma-ray burst could explain these patterns. The initial radiation pulse would have photodissociated atmospheric nitrogen and oxygen, creating nitrogen oxides that rapidly depleted stratospheric ozone. Without this protective layer, lethal ultraviolet radiation would have penetrated Earth's oceans to depths exceeding 25 meters, sterilizing the photic zone where most marine organisms lived. The resulting atmospheric chemistry changes would have triggered acid rain and global cooling, as sulfur compounds blocked incoming solar radiation. The Spitzer Space Telescope's infrared observations have identified Wolf-Rayet stars within our local galactic neighborhood that match the stellar classifications associated with gamma-ray burst progenitors. WR104 in Sagittarius, WR124 and Boets, and several others represent potential hypernova candidates within striking distance of Earth. These stars, with masses exceeding 40 times that of our Sun, exhibit the rapid mass loss and chemical enrichment signatures that theoretical models predict will culminate in core collapse within the next few million years. Yet fundamental questions persist about this cosmic catastrophe. How did life recover so dramatically after such devastation, with the Silurian period witnessing an explosive radiation of new species forms? Why do some gamma-ray burst models predict complete sterilization of the biosphere, while others suggest selective extinction patterns? Could the Earth's magnetic field have provided sufficient protection against the initial radiation pulse? What would happen if a similar burst occurred today, with our current atmospheric composition and ozone concentrations? The mathematical precision of stellar death carries implications that extend far beyond paleontology into the realm of astrobiology itself. The Permian-Triassic extinction. You are standing on the edge of what will become Siberia 252 million years ago. The ground beneath your feet convulses. Not an earthquake, something deeper. The entire continental plate is fracturing from below. Molten rock begins hemorrhaging through cracks that stretch for thousands of kilometers. This is not a volcano. This is the planet bleeding. The Siberian traps represent the largest known volcanic event in Earth's history. Between 252 and 250 million years ago, this flood basalt province erupted continuously for approximately 2 million years. The lava flows covered an area roughly the size of the continental United States, creating rock formations up to 6 kilometers thick in some regions. Dr. Paul Wignall of the University of Leeds published research in geology in 2009 demonstrating that these eruptions release an estimated 15 million cubic kilometers of basaltic magma onto Earth's surface. But the lava was not the killer. The gas was. Studies by Dr. Henrik Svensson at the University of Oslo, published in Earth and Planetary Science Letters in 2009, calculated that the Siberian traps released between 30,000 and 100,000 gigatons of carbon dioxide into the atmosphere over their active period. For context, current annual human carbon dioxide emissions total approximately 40 gigatons. The volcanic emissions also included massive quantities of sulfur dioxide, hydrogen sulfide, and methane. The atmospheric chemistry transformed Earth into a furnace. Paleoclimate reconstructions by Dr. Yadong Sun and colleagues, published in Science in 2012, indicate that global average temperatures rose by 8 to 10 degrees Celsius. Ocean temperatures reached 40 degrees Celsius in some regions. The pH of seawater dropped dramatically as carbon dioxide dissolved into carbonic acid, creating conditions so acidic that calcium carbonate shells simply dissolved. The biological toll was unprecedented. The Permian-Triassic extinction event eliminated 96% of all marine species and 70% of all terrestrial vertebrate species. Dr. Douglas Irwin of the Smithsonian Institution has called it the mother of all mass extinctions. Entire taxonomic orders vanished completely. Trilobites, which had survived every previous extinction event for 270 million years, finally disappeared forever. Here's what makes this impossible. Volcanoes erupt. They release gas. They change climate temporarily. But the Siberian traps operated on a scale that breaks our understanding of planetary systems. The standard geological model says that flood basalt provinces result from massive upwellings of hot mantle material called superplumes. These thermal anomalies rise from deep within Earth's interior, possibly from the core mantle boundary, and create sustained volcanic activity when they reach the surface. But the data doesn't support a simple superplume origin. The Siberian traps erupted with a violence and duration that exceeds what thermal plume models can explain. Dr. Scott Bryan of the Queensland University of Technology published research in Nature Geoscience in 2010 showing that the initial eruption phase released more magma in less than 1 million years than most flood basalt provinces produce in their entire lifespans. The chemical composition of the magmas also indicates multiple sources, not a single rising plume. Some researchers propose that the Siberian traps were triggered by an external impact event. Dr. Luann Becker of the University of California, Santa Barbara, published controversial evidence in Science in 2001, suggesting that fullerenes containing trapped noble gases with extraterrestrial isotopic signatures were present in Permian-Triassic boundary rocks. This could indicate that a massive asteroid or comet impact destabilized the mantle beneath Siberia, triggering the volcanism. Others suggest that the volcanism was part of a cascading planetary catastrophe. Dr. Peter Ward of the University of Washington has proposed that the massive carbon dioxide release created a runaway greenhouse effect that melted methane hydrates buried in ocean sediments. This released additional greenhouse gases, creating a positive feedback loop that amplified the warming beyond what volcanism alone could achieve. The timing presents another puzzle. Radiometric dating by Dr. Seth Burgess of the United States Geological Survey, published in Science Advances in 2017, shows that the most intense phase of Siberian volcanism coincided almost exactly with the extinction event. But volcanic provinces typically take millions of years to build up to peak activity. Why did this one reach maximum intensity so quickly? What force could sustain volcanic activity for 2 million years straight? How did a single province release more carbon dioxide than exists in Earth's current atmosphere? Why did the extinction occur so rapidly when climate change should have allowed some adaptation time? What prevented the usual recovery mechanisms that restored biodiversity after previous extinction events? Could such sustained volcanism happen again? The Siberian traps fell silent 250 million years ago, but their scars remain written in rock layers worldwide. Yet, even as Earth slowly recovered from this volcanic apocalypse, another catastrophe was already brewing in the depths of space: the Late Heavy Bombardment. You are standing on the surface of early Earth 4 billion years ago, but there is no ground beneath your feet. There's only molten rock and superheated steam. Above you, the sky burns orange with incoming asteroids the size of Manhattan. Each impact releases the energy of 10 million hydrogen bombs. The oceans boil away completely every few thousand years. This is not science fiction. This is what the Apollo lunar samples revealed actually happened to our planet for 300 million years straight. The evidence came from the moon. When Apollo 11, 12, 14, 15, 16, and 17 brought back 842 pounds of lunar rock between 1969 and 1972, geochemists at the Johnson Space Center found something extraordinary in the samples. The Highland rocks contained impact melt signatures dating to a narrow window, 4.1 to 3.8 billion years ago. Every single Highland sample from different regions of the moon showed massive bombardment during this exact same period. Dr. Graham Ryder of the Lunar and Planetary Institute published the definitive analysis in Earth and Planetary Science Letters in 2000. His isotopic dating revealed that lunar impact basin formation spiked by a factor of 50 during this 300 million year window. The Imbrium Basin, Oriental Basin, and Crisium Basin all formed within this period. But here's what makes this catastrophic. If the moon experienced this bombardment intensity, Earth received 20 times more impacts due to its larger gravitational cross-section and closer proximity to the asteroid belt. Computer simulations by Alessandro Morbidelli at the Côte d'Azur Observatory, published in Nature in 2005, modeled the orbital mechanics. The NICE model shows Jupiter migrating inward toward the Sun, then suddenly reversing course and moving outward. This migration destabilized the asteroid belt, hurling approximately 10 million asteroids larger than 1 kilometer directly toward the inner solar system. The largest impactors exceeded 100 kilometers in diameter. Each major impact vaporized Earth's oceans completely. The energy release from a 1-100 kilometer asteroid striking at 25 kilometers per second equals 50 million megatons of TNT. This heats the entire atmosphere to over 2,000 Kelvin, turning water into superheated steam that escapes to space. Ocean reformation required thousands of years between impacts. During the peak bombardment period, this cycle repeated continuously. The standard cosmological model explains the late heavy bombardment as a natural consequence of planetary migration in young solar systems. The NICE model demonstrates how gravitational resonances between Jupiter and Saturn could destabilize the outer solar system, sending debris inward. The lunar crater record supports this timeline perfectly. The bombardment ended when the asteroid belt achieved its current stable configuration. But the survival mechanism remains unexplained. How did early life persist through ocean vaporizing impacts every few thousand years? Radiometric dating of zircon crystals in Western Australia, published by Mark Harrison at the University of California, Los Angeles, in Proceedings of the National Academy of Sciences in 2008, shows liquid water existed on Earth throughout this entire bombardment period. The isotopic signatures in 4.4 billion-year-old zircons indicate temperatures consistent with liquid oceans. Some astrobiologists suggest life retreated to deep crustal environments during each impact cycle. The subsurface biosphere could have survived in rock fractures kilometers below the surface, protected from surface sterilization events. Others propose that life repeatedly originated from scratch after each major impact, evolving from organic compounds in the cooling oceans. Recent analysis by Simone Marchi at the Southwest Research Institute, published in Earth and Planetary Science Letters in 2014, calculated the exact impact flux. During peak bombardment, Earth received approximately 17,000 impacts from asteroids larger than 1 kilometer every million years. Each impact larger than 10 kilometers triggered global climate disruption lasting decades. Impacts larger than 50 kilometers caused complete atmospheric loss. The late heavy bombardment represents the most sustained catastrophe in Earth's history. For 300 million years, our planet existed in a state of continuous destruction and renewal. The fact that life not only survived, but established the foundation for complex biochemistry during this period challenges every model of planetary habitability. How did organic molecules remain stable during repeated ocean vaporization? What protected early genetic systems from impact-generated temperatures exceeding the boiling point of rock? Could life have actually required this bombardment to evolve complex metabolic pathways? Why did the bombardment end so abruptly, exactly when it did? The asteroids that nearly destroyed Earth 4 billion years ago pale in comparison to what electromagnetic radiation from our own sun would unleash on our technological civilization just 164 years ago. The Carrington event. You are staring at telegraph wires that have become incandescent snakes writhing across the countryside. September 1st, 1859, Boston. The operator beside you has disconnected his battery an hour ago, but the messages keep flowing. The wires are drawing power directly from the sky. Sparks cascade from every metal contact. Telegraph poles burst into flame across New England. In Havana, Cuba, 24 degrees north of the equator, green and red curtains of light dance overhead like the aurora has forgotten where it belongs. This is impossible. The Earth's magnetic field doesn't collapse. Not like this. The morning before, British astronomer Richard Carrington was projecting the sun's image through his telescope at his private observatory in Red Hill, Surrey. At 11:18 local time, he witnessed something no human had ever documented: 2 brilliant white ribbons of light erupting from a cluster of sunspots. The flare lasted exactly 5 minutes. Carrington sketched what he saw, noting the precise coordinates on the solar disk. He was observing the most powerful solar flare in recorded history, a coronal mass ejection that hurled billions of tons of charged particles toward Earth at speeds exceeding 1,600 kilometers per second. 18 hours later, those particles slammed into our magnetosphere with unprecedented force. The Carrington event, as it came to be known, compressed Earth's magnetic field to half its normal distance from the planet's surface. Telegraph systems across North America and Europe either failed completely or began operating without external power sources. In some locations, telegraph operators received electric shocks strong enough to knock them unconscious. The electromagnetic pulse was so intense that telegraph lines in Boston continued transmitting messages for 2 hours after being disconnected from their power sources. The aurora, normally confined to latitudes above 60 degrees, appeared as far south as Rome, Hawaii, and the Caribbean. Gold miners in the Rocky Mountains woke believing dawn had broken, so bright were the northern lights overhead. In New York City, people read newspapers by aurora light at 2 in the morning. The phenomenon was visible across the entire continental United States, with reports of red, green, and purple curtains stretching from horizon to horizon. But here's what makes the Carrington event genuinely catastrophic in modern terms. The electromagnetic disruption that crippled 19th century telegraph lines would devastate our current technological infrastructure. The National Academy of Sciences published a comprehensive analysis in 2008 detailing the potential damage from a Carrington-class event occurring today. The electromagnetic pulse would destroy power grid transformers across entire continents. Satellite navigation systems would fail. Communication networks would collapse. The economic damage would exceed $2 trillion in the United States alone, with recovery requiring 4 to 10 years. The standard solar physics model explains coronal mass ejections as magnetic field line reconnection events. Solar plasma, heated to 10 million Kelvin, becomes trapped in magnetic loops extending thousands of kilometers above the sun's surface. When these field lines snap and reconnect, they release energy equivalent to billions of nuclear weapons, hurling charged particles into space at relativistic speeds. Earth's magnetosphere, the magnetic field bubble surrounding our planet, normally deflects most of this solar wind, channeling particles toward the poles where they create the familiar aurora. But the Carrington event's intensity challenges our understanding of maximum solar output. The flare released energy equivalent to 10 billion 1 megaton nuclear weapons detonating simultaneously. Current solar physics models struggle to explain how the sun can store and release this magnitude of magnetic energy. The event occurred during solar cycle 10, which wasn't even a particularly active solar maximum. Some astrophysicists suggest we may be underestimating the sun's capacity for extreme magnetic reconnection events. Ice core data from Greenland and Antarctica reveals evidence of even more powerful solar storms in Earth's distant past. Isotope analysis indicates events in 775 and 994 that produce cosmic ray spikes significantly larger than the Carrington event. These prehistoric solar storms occurred during periods of low solar activity, suggesting our understanding of the solar magnetic cycle may be fundamentally incomplete. The most unsettling aspect isn't the historical record, it's the statistical inevitability. Solar physicists calculate that Carrington-class events occur approximately once every 150 years. We're now 164 years past the last one. The probability of another Carrington event occurring within the next 50 years exceeds 50%, yet our technological civilization remains completely unprepared for electromagnetic disruption of this magnitude. What happens when our satellite-dependent civilization faces solar fury that makes nuclear weapons look gentle? How long can modern society function without electrical power grids, communication networks, or GPS navigation? Why do ice core records suggest even more powerful solar storms await us? Could the sun's magnetic field be capable of variations that would make the Carrington event look modest? And if such storms have struck Earth before, what prevented them from stripping away our atmosphere entirely? The Earth's geological record holds evidence of catastrophes that dwarf even solar storms in their capacity to reshape the biosphere. The Toba supervolcano eruption. You are standing on the shores of what will one day become Lake Toba in northern Sumatra. The year is 74,000 BCE. The morning air carries an unusual sulfuric tang. Birds have gone silent. The ground beneath your feet trembles with a rhythm that seems to come from the planet's core itself. Then the mountain tears itself apart. Mount Toba erupts with a force of 1 billion Hiroshima bombs detonating simultaneously. 2,800 cubic kilometers of magma, rock, and ash blast into the stratosphere at supersonic speeds. The explosion registers as a magnitude 8.8 on the Volcanic Explosivity Index, the most powerful eruption in the last 2 million years. The sound carries across continents. The ash plume rises 40 kilometers into the sky, punching through the stratosphere and spreading across both hemispheres. Within hours, volcanic debris begins raining down across South and Southeast Asia. Ash layers 15 centimeters thick blanket India. The Bay of Bengal turns black with pumice. But the immediate devastation is only the beginning. The eruption injects 6 billion tons of sulfur dioxide into the upper atmosphere, where it combines with water vapor to form sulfuric acid aerosols. These particles reflect incoming solar radiation back into space, triggering a volcanic winter that will last for decades. Global temperatures plummet by 3 to 5 degrees Celsius. In some regions, the cooling reaches 10 degrees. Monsoons fail, forests die, lakes freeze. The planet enters what researchers call a nuclear winter scenario, but one lasting not months, but years. Stanley Ambrose of the University of Illinois published his analysis in the Journal of Human Evolution in 1998, proposing that this climate catastrophe created a population bottleneck so severe it nearly extinguished our species. Genetic evidence supports this terrifying possibility. Studies of mitochondrial DNA diversity, published by Spencer Wells and his colleagues, suggest that the entire human population collapsed to between 3,000 and 10,000 breeding individuals. Every person alive today descends from this tiny group of survivors. The Toba eruption, according to this model, brought humanity closer to extinction than any other single event in our history. The standard geological model explains supervolcanic eruptions as the inevitable result of massive magma chamber dynamics. Beneath Toba, a colossal reservoir of molten rock accumulated over hundreds of thousands of years. As the chamber filled, pressure increased until the overlying rock could no longer contain it. The eruption was catastrophic but predictable, a natural consequence of plate tectonics and crustal dynamics. The climate effects, while severe, fall within known parameters for large volcanic events. Recovery was certain, just delayed. But the genetic bottleneck data reveals something the geological model cannot fully explain. Modern humans had already migrated out of Africa and established populations across Eurasia by 74,000 years ago. Archaeological evidence from sites like Pinnacle Point in South Africa and Jwalapuram in India shows continuous human occupation before, during, and after the Toba eruption. Some populations appear to have survived the volcanic winter with minimal genetic impact. Others vanished entirely from the archaeological record. How did scattered groups of early humans, equipped with Stone Age technology, survive a climate catastrophe that modern climate models suggest should have been unsurvivable? Some archaeologists propose that human populations had already developed sophisticated survival strategies, controlled use of fire, food storage, complex social networks that allowed them to weather the volcanic winter. Others suggest that regional climate variations created refugia where small groups could persist. A minority of researchers propose that the genetic bottleneck preceded the Toba eruption and that volcanic winter simply accelerated an already occurring population decline. Recent studies of the Toba ash layers reveal another puzzle. The volcanic debris shows evidence of multiple explosive phases separated by weeks or months. This wasn't a single cataclysmic event, but a series of eruptions that may have lasted for years. Each phase would have reloaded the atmosphere with fresh aerosols, extending the volcanic winter far beyond standard models. Yet somehow, somewhere, humans not only survived, but retained enough genetic diversity to eventually repopulate the planet. The Lake Toba caldera today measures 100 kilometers long and 30 kilometers wide, the largest volcanic crater on Earth. Core samples from the lake bottom reveal sediment layers that chronicle the eruption's aftermath. Decades of reduced biological productivity, failed seasonal cycles, ecosystem collapse, and gradual recovery. The geological record is clear. The human story remains fragmentary. What survival strategies allowed a few thousand individuals to endure a planetary catastrophe? How did scattered populations maintain the genetic diversity necessary for species recovery? Why did some human groups vanish while others persisted? Could modern civilization survive a similar event? And perhaps most unsettling, when will the Toba magma chamber reach critical pressure again? But supervolcanic eruptions are not the only planetary catastrophes preserved in Earth's geological record. The Chicxulub impact. You're standing on what will become the Yucatan Peninsula, 66 million years ago. The morning sky stretches endless blue above a world dominated by giants. Triceratops herds move through fern prairies. Tyrannosaurus rex stalks through ancient forests. Marine reptiles longer than school buses patrol warm, shallow seas. The air hums with insects the size of dinner plates. Then you see it. A pinprick of light in the northern sky, growing brighter by the second. In the next 6 minutes, this 10-kilometer wide chunk of rock and metal will end the Mesozoic era forever. The Chicxulub impactor struck Earth at approximately 20 kilometers per second, roughly 60 times faster than a rifle bullet. The impact site, discovered by geophysicist Glenn Penfield while analyzing magnetic anomaly data for Pemex in 1978, sits buried beneath the northwestern edge of Mexico's Yucatan Peninsula. The crater spans 150 kilometers in diameter, with a peak ring structure extending to 200 kilometers. Shocked quartz grains minerals that can only form under pressures exceeding 10 gigapascals appear in rock layers exactly at the Cretaceous-Paleogene boundary, dated to 66.04 million years ago by radiometric analysis of volcanic ash layers. Luis Alvarez and his son Walter published their revolutionary paper in Science Journal in 1980, proposing that an extraterrestrial impact caused the mass extinction event that eliminated non-avian dinosaurs. Their evidence centered on an anomalous concentration of iridium, an element rare in Earth's crust but abundant in asteroids found in boundary clay layers at Gubbio, Italy. Subsequent drilling by the Chicxulub Scientific Drilling Project in 2016 penetrated the peak ring, recovering samples of impact melt rock and shocked minerals that confirmed the catastrophic nature of the collision. The energy release defies comprehension. Conservative estimates place the impact at 10 billion times the energy of the atomic bombs dropped on Hiroshima and Nagasaki combined. The explosion instantly vaporized thousands of cubic kilometers of limestone and sulfate-rich bedrock, hurling molten debris into ballistic trajectories that reached the edge of space before raining back down as glass spherules across North America. Seismic waves equivalent to magnitude 11 earthquakes circled the globe multiple times. The impact generated temperatures exceeding 10,000 Kelvin at ground zero, hot enough to vaporize rock and create a fireball visible from orbit. But the immediate destruction was only the beginning. The impact ejected an estimated 25 trillion tons of debris into the stratosphere, creating a global dust cloud that blocks sunlight for months. Surface temperatures plummeted by as much as 26 degrees Celsius in the impact winter that followed. Photosynthesis shut down across terrestrial and marine ecosystems. Food chains collapsed from the bottom up. The vaporized sulfate bedrock produced acid rain with a pH low enough to dissolve limestone. Massive wildfires, triggered by the re-entry of molten ejecta, consumed forests across multiple continents. The mainstream scientific consensus attributes the end Cretaceous mass extinction, which eliminated roughly 75% of all species on Earth, primarily to this single asteroid impact. The temporal correlation between the Chicxulub impact and the extinction boundary appears precise within the resolution of current dating methods. The global distribution of shocked minerals, impact spherules, and iridium anomalies supports a worldwide environmental catastrophe triggered by the collision. But the complete picture remains more complex than a simple impact scenario can explain. The Deccan Traps in India were simultaneously erupting in one of the largest volcanic episodes in Earth's history, releasing massive quantities of sulfur dioxide and carbon dioxide into the atmosphere over hundreds of thousands of years. Some paleontologists argue that dinosaur diversity was already declining before the impact, suggesting multiple stressors were weakening ecosystems. The extinction pattern itself shows puzzling selectivity. Freshwater organisms survived at higher rates than marine species, despite marine environments being theoretically more buffered against rapid environmental change. Marine ecosystems collapsed almost entirely, yet many small mammals, birds, crocodilians, and turtles survived the extinction boundary. Some researchers propose that the impact acted as the final blow to ecosystems already stressed by climate change, volcanism, and sea level fluctuations. Others suggest that multiple impact events occurred within a geologically brief time window, though evidence for additional large craters of the same age remains inconclusive. Recent analysis of the drill core samples reveals that the impact occurred in spring in the northern hemisphere, based on the growth patterns of fossil fish found at the Tanis site in North Dakota. The precision of this timing data demonstrates how a single moment in deep time can now be reconstructed with seasonal accuracy. How did life recover from such complete devastation? What determined which lineages survived while others vanished forever? Why did the impact trigger such rapid evolutionary innovation in the surviving species? Could similar devastation occur again, and would intelligence provide any advantage against cosmic catastrophe? Why does Earth's history seem punctuated by these moments when everything almost ends? Yet mass extinctions, as catastrophic as they appear, sometimes clear the stage for even more dramatic transformations of life itself. The Great Oxygenation Event. You are standing on the shores of an alien Earth 2.4 billion years ago. The sky above you is not blue, but a pale orange-pink, heavy with methane and hydrogen sulfide. The ocean stretches endlessly before you, its surface a carpet of green and purple bacterial mats that pulse with ancient life. The air itself would kill you in seconds, not from lack of oxygen, but from its complete absence. This is a world that has thrived for over 1 billion years without a single breath of the gas that sustains every complex life form on modern Earth. Then, in the shallow waters at your feet, something begins to change. Microscopic blue-green organisms called cyanobacteria start performing a chemical trick that will transform this planet forever. They begin splitting water molecules and releasing oxygen as waste. In less than 200 million years, this toxic byproduct will poison nearly 90% of all life on Earth and plunge the entire planet into the longest ice age in its history. The Great Oxygenation Event represents the most catastrophic biogenic extinction in Earth's geological record, documented through isotopic analysis in banded iron formations across every continent. Geochemist Preston Cloud first identified the evidence in 1972 while studying iron ore deposits in the Lake Superior region. The Geological Survey of Western Australia later confirmed the global scope through drilling cores that revealed a sharp transition in sulfur isotope ratios at exactly 2.4 billion years ago. The Archean Eon, which had maintained a reducing atmosphere for over 1 billion years, ended abruptly when oxygen concentrations rose from less than 1 part per million to over 1% of the atmosphere. Here's what makes this impossible to comprehend. Cyanobacteria, organisms smaller than the width of a human hair, generated enough oxygen to fundamentally alter the chemistry of an entire planet. NASA's Astrobiology Institute calculates that these microbes produced over 10 to the power of 15 kilograms of oxygen annually during peak production phases. The oxygen concentration in Earth's atmosphere increased by a factor of 10,000 in what geologists consider an instant 200 million years. For perspective, this is equivalent to every breath of air on modern Earth being replaced with pure oxygen in the span of a single afternoon on geological timescales. The standard geological model explains this event as an inevitable consequence of photosynthetic evolution. Cyanobacteria developed the ability to use water as an electron donor in photosynthesis, splitting hydrogen from oxygen and releasing the oxygen as waste. Initially, this free oxygen was absorbed by dissolved iron in the oceans, creating the massive banded iron formations we observe today. Once the iron was saturated, oxygen began accumulating in the atmosphere. The model suggests this was a gradual process driven by evolutionary advantage organisms that could harness the abundant energy from sunlight, would naturally outcompete those dependent on scarce chemical energy sources. But the data reveals complications this explanation cannot address. Stromatolite fossils from the Pilbara Craton in Western Australia show that cyanobacteria existed for at least 300 million years before the Great Oxygenation Event began. Why did oxygen production remain negligible for so long, then suddenly accelerate to planetary scales? The University of Washington's Earth and Space Sciences Department has identified what they term whiff events, brief oxygen spikes occurring hundreds of millions of years before the main event. suggesting the process was neither gradual nor inevitable. Some biogeochemists propose that the timing correlates with tectonic shifts that expose vast new surface areas for bacterial colonization. Others suggest that genetic mutations in cyanobacteria suddenly made oxygen production more efficient. A minority of researchers argue that external factors, possibly increased solar radiation or cosmic ray bombardment, triggered the explosive growth of oxygen-producing organisms. The consequences bordered on planetary sterilization. Free oxygen was literally toxic to the anaerobic organisms that dominated Earth's biosphere. Their cellular machinery evolved over billions of years to function in reducing conditions, was destroyed by oxidation. The methane that had maintained Earth's greenhouse effect was broken down by atmospheric oxygen, causing global temperatures to plummet. The planet entered what geologists call the Huronian glaciation ice sheets, extending from pole to pole for 300 million years. Ice core analogs from this period, preserved in South African rock formations, indicate that equatorial temperatures dropped below minus 40 degrees Celsius. Life on Earth came within an evolutionary hair's breadth of complete extinction. What drove the most successful organisms on the planet to poison their own environment so completely? Why did natural selection favor a process that would destroy the very ecosystem these organisms depended upon? How did any life survive 300 million years of global ice and toxic atmospheric conditions? Could a similar catastrophic transition be occurring in Earth's biosphere today, too slowly for us to recognize? Why do the most creative forces in the universe seem to operate through near total destruction? The answers may lie buried in ice cores, from an event that occurred much more recently, when another catastrophic change reshaped Earth's climate in the span of mere millennia: the Younger Dryas impact. You are standing in what will become the Great Lakes region 12,900 years ago. The sky above you burns with fragments of light, not meteors, something larger. A disintegrating comet, its nucleus shattered into thousands of pieces across millions of kilometers of space, rains down across the North American ice sheet. Each impact releases energy equivalent to hundreds of nuclear weapons. The Laurentide ice sheet, 2 kilometers thick, begins to crack and surge. Within decades, the world will plunge back into an ice age that lasts 1,000 years. The megafauna woolly mammoths, giant ground sloths, saber-toothed cats will vanish from 2 continents. Human populations will collapse by 90%. The Younger Dryas period, documented through ice core analysis by researchers at the University of Copenhagen and published in the Journal of Quaternary Science in 2007, represents one of the most dramatic climate reversals in Earth's recent history. Between 12,900 and 11,700 years ago, global temperatures plummeted by an average of 15 degrees Celsius in less than a decade. The event coincides precisely with what geologists call the Younger Dryas boundary layer, a distinct geological stratum found across North America, Europe, and parts of Asia. This boundary layer contains extraordinary evidence. Platinum concentrations spike to levels 300 times higher than background readings. Microscopic diamonds, formed only under extreme pressure and temperature, appear in quantities that dwarf any natural terrestrial process. Glass spherules, tiny beads of melted rock, scatter across the layer in densities reaching 50,000 per square meter. Nanodiamonds, carbon structures that require pressures exceeding 100 gigapascals to form, appear alongside fullerenes containing extraterrestrial helium isotopes. The Comet Research Group, led by nuclear chemist Richard Firestone of Lawrence Berkeley National Laboratory and published in the Proceedings of the National Academy of Sciences, documented these impact markers across 51 sites, spanning 4 continents. The platinum anomaly alone suggests the deposition of extraterrestrial material equivalent to a comet nucleus 10 kilometers in diameter. But the geographic distribution indicates not a single impact, but multiple airbursts and ground strikes across a swath of territory, covering 13 million square kilometers. Here's what makes this catastrophic. The energy release calculations, performed by physicist Alan West and published in the Journal of Geology in 2013, suggest a total impact energy exceeding 10 to the 23rd joules, equivalent to 10 million megatons of explosives detonating simultaneously across North America. The thermal pulse would have ignited biomass across the continent, creating continent-wide wildfires that pumped enough soot into the atmosphere to block sunlight for months. The impact on the Laurentide ice sheet would have released catastrophic freshwater floods into the North Atlantic, disrupting thermohaline circulation and triggering the abrupt return to glacial conditions. The standard geological model says the Younger Dryas resulted from natural climate variability. Meltwater pulses from retreating glaciers disrupted ocean circulation patterns, triggering the climate reversal through well-understood feedback mechanisms. The megafaunal extinctions resulted from human hunting pressure combined with rapid climate change at the end of the last ice age. The geological markers represent terrestrial processes, wildfires, volcanic activity, and normal cosmic dust accumulation concentrated through natural processes. But the isotopic signatures don't support terrestrial origins. The platinum group element ratios match chondritic meteorites, not terrestrial or volcanic sources. The nanodiamonds contain Lonsdale-like structures that form only during hypervelocity impacts exceeding 20 kilometers per second. The glass spherules show chemical compositions identical to those produced in nuclear weapons testing, requiring temperatures exceeding 2000 Kelvin to form. Most critically, radiocarbon dating of the extinction horizon shows that 35 genera of North American megafauna disappeared within a span of less than 300 years, synchronized with the impact markers to within dating uncertainties. Some planetary scientists suggest we're looking at evidence of the most recent major impact event in human history. The fragmentation pattern indicates the parent body, likely a comet from the outer solar system, began breaking apart while still approaching Earth. Computer models by astronomer Bill Napier, published in monthly notices of the Royal Astronomical Society, show how a single large comet nucleus could produce the observed geographic distribution of impact sites through atmospheric fragmentation and multiple ground strikes. The magnetic field evidence compounds the mystery. Paleomagnetic analysis of the boundary layer shows magnetic minerals aligned in chaotic orientations, suggesting the presence of powerful electromagnetic fields during the impact event. Some researchers propose that the electrical discharge from multiple comet fragment impacts created electromagnetic pulses sufficient to disrupt the planet's magnetic field locally, leaving permanent magnetic signatures in the geological record. Why did this particular comet fragment so extensively before impact? How did the synchronized impacts trigger such precise climatic feedback loops? Could fragments of the same parent body still orbit in Earth-crossing trajectories? What prevented similar fragmentation events during other periods of comet bombardment? If atmospheric entry caused the fragmentation, why don't we see similar signatures from other large impactors? The approaching entry on magnetic field reversals suggests that Earth's protective systems can fail more dramatically than most realize. The Lachamp geomagnetic excursion. You are standing in the ancient forests of Germany 41,000 years ago, and above you, the northern lights are dancing at the equator. Green curtains of radiation sweep across tropical skies that have never seen aurora. The magnetic compass in your hand spins wildly, unable to find north, because north has ceased to exist. The invisible shield that has protected life on this planet for billions of years is collapsing, and every living cell is about to be bathed in the sterilizing fire of deep space. The Lachamp geomagnetic excursion was first discovered in 1969 by French geophysicist Bernard Brunhes at the Institute of Physics of the Globe in Paris. Studying volcanic rocks from the Lachamp lava flows in the Massif Central, Brunhes found magnetic minerals that pointed in the wrong direction entirely. Further analysis by paleomagnetist Norbert Bonhamet revealed these rocks had formed during a period when Earth's magnetic field had not just weakened, but had attempted to flip completely. Radiocarbon dating placed this event at precisely 41,400 years ago, lasting for approximately 1,600 years. The European Space Agency's SWARM mission, launched in 2013, has mapped the precise mechanics of what happened. Earth's magnetic field strength dropped to just 10% of its normal intensity. The magnetic poles wandered across the surface like lost travelers, with the North Magnetic Pole drifting as far south as the equator before attempting to establish itself near present-day Antarctica. Core samples from the Greenland ice sheet, analyzed by researchers at the University of Copenhagen in 2021, show cosmic ray flux increased by a factor of 3 during this period. The atmosphere was being stripped away, particle by particle. Tree ring data from German oak forests, studied by radiocarbon specialist Florian Adolphi at Lund University, reveals that carbon-14 levels spiked to their highest concentrations in 50,000 years. This isotope forms only when cosmic rays collide with nitrogen in the upper atmosphere. The trees were recording a cosmic radiation bombardment that should have sterilized the planet's surface. Sediment cores from Lake Mono in California show elevated levels of beryllium-10, another cosmogenic isotope, confirming that the entire planet was exposed to radiation levels normally found only in the vacuum of space. The mainstream scientific consensus explains geomagnetic excursions as natural variations in Earth's dynamo system. The molten iron core generates electric currents that produce our magnetic field, and occasionally these currents become unstable. Computer models, developed by the Max Planck Institute for Solar System Research, suggest these events occur roughly every 200,000 years as part of the normal geodynamo process. The magnetic field weakens, the poles wander, and eventually the system restabilizes. Life survives because the excursions are temporary, lasting only a few thousand years at most. But the Lachamp event reveals something the standard model cannot fully explain. DNA analysis of Neanderthal remains from this precise time period, conducted by the Max Planck Institute for Evolutionary Anthropology, shows evidence of massive population bottlenecks. Neanderthal populations across Europe collapsed to near extinction levels exactly 41,000 years ago. Modern human migration patterns, traced through mitochondrial DNA by researchers at the University of Cambridge, show our species retreated into caves and deep valleys during the same window. Some paleoanthropologists suggest the magnetic field collapse may have driven both species to develop the first sophisticated cave art as they sheltered from the cosmic radiation above. Ice core data from Antarctica reveals that during the Lachamp excursion, atmospheric ozone levels dropped by 60%. Without ozone protection, ultraviolet radiation from the sun reached the surface at levels that caused DNA damage within minutes of exposure. Yet somehow, life not only survived, but potentially evolved new adaptive mechanisms during this period. Archaeological evidence from Blombos Cave in South Africa shows the first appearance of complex symbolic behavior in modern humans dates to exactly this time frame. Some evolutionary biologists propose that the radiation pressure may have accelerated mutation rates, driving rapid cognitive evolution in surviving populations. What kind of cosmic lottery allowed complex life to survive a 1,000-year bombardment of sterilizing radiation? Why did this magnetic collapse coincide with the most significant behavioral changes in human evolution? How did Earth's biosphere recover so completely that no trace remains in the fossil record? Could similar magnetic field instabilities explain other mass extinction events where the cause remains unknown? What does the fact that we are here today tell us about life's resilience in the face of planetary-scale catastrophe? As we map the wandering of ancient magnetic poles, another cosmic threat emerges from the constellation Sagittarius, where a massive star prepares for its final performance. Ruser 104. You are calibrating the Keck Observatory's adaptive optics system on Mauna Kea, Hawaii, in March 2008. The infrared detectors lock onto a target 8,000 light-years away in the constellation Sagittarius. What appears on your screen is a perfect spiral structure rotating in space, a cosmic pinwheel of superheated gas and stellar material. Beautiful, elegant, and aimed directly at Earth like the barrel of the most powerful weapon in the universe. The Wolf-Rayet star WR104 sits at the center of this spiral, cataloged first by the Wide Field Infrared Survey Explorer and studied intensively by the Very Large Telescope in Chile. Dr. Peter Tuthill of the University of Sydney and his team published their analysis in the Astrophysical Journal in 2008, confirming what ground-based observations had suggested. This star system rotates with its axis of rotation pointing within 15 degrees of our solar system. The companion star, locked in a tight 8-month orbit, strips material from WR-104 at velocities exceeding 1,000 kilometers per second. The ejected material forms a spiral pattern extending outward for over 100 astronomical units, a structure so precise it resembles a cosmic nautilus shell frozen in time. WR-104 belongs to a class of stars that represent stellar evolution in its most violent phase. With a mass 25 times that of our Sun, compressed into a radius only 5 times larger, this star burns through its nuclear fuel at a rate that makes our Sun appear dormant. Surface temperatures exceed 50,000 Kelvin, nearly 9 times hotter than the Sun's surface. The stellar winds carry away 3 solar masses of material every million years, a mass loss rate 10 million times greater than our Sun's solar wind. These are not gentle stellar breezes. These are hurricane-force gales of plasma traveling at 2,000 kilometers per second, carrying enough energy to power our entire civilization for billions of years. Here's what makes this impossible to ignore. WR-104 will die as a hypernova within the next 500,000 years, potentially much sooner. When it does, the collapse of its core will release more energy in the first 10 seconds than our Sun will produce in its entire 10 billion year lifetime. That energy will focus into 2 narrow beams of gamma radiation, each beam containing the concentrated power output of 1 trillion suns. The rotation axis of WR-104, the axis along which these gamma ray beams will fire, points directly toward Earth with an uncertainty of only plus or minus 16 degrees. The standard cosmological model says that gamma ray bursts from hypernovas pose no significant threat to life on Earth beyond distances of several thousand light-years. At 8,000 light-years, the inverse square law should dissipate the gamma radiation to levels that might damage our ozone layer but not cause immediate mass extinction. Computer simulations by Dr. Adrian Malott at the University of Kansas suggest that a hypernova at this distance would deplete 25% of Earth's ozone layer, potentially triggering climate changes but allowing most life to survive. The spiral structure visible in the WR-104 system indicates the gamma ray burst would likely be less focused than those from single-star collapses, further reducing the threat level. But recent observations by the Hubble Space Telescope reveal details that don't fit this reassuring picture. The spiral structure extends much farther from the central binary than theoretical models predict, suggesting magnetic fields strong enough to collimate the eventual gamma ray burst into a tighter beam than initially calculated. Dr. Grant Hill's analysis of the system's infrared emissions, published in Monthly Notices of the Royal Astronomical Society in 2016, shows that WR-104 may have retained more of its hydrogen envelope than typical Wolf-Rayet stars, potentially creating a hypernova explosion rather than a standard gamma ray burst. Hypernovas release 10 to 100 times more energy than regular gamma ray bursts. Some astrophysicists suggest that at 8,000 light-years, a hypernova beam pointed directly at Earth could deliver enough gamma radiation to strip away our entire ozone layer within hours, sterilizing the planet's surface under unfiltered ultraviolet radiation from the Sun. The Spitzer Space Telescope's observations show that the companion star's orbit may be decaying faster than expected, potentially accelerating WR-104's timeline toward collapse. Radio telescope arrays have detected periodic variations in the system's emissions that suggest the central star may already be approaching the final stages of nuclear burning in its core. What happens when 8,000 light-years becomes close enough? How do we prepare for a threat that could arrive tomorrow or in 500,000 years? Can a civilization develop contingencies for cosmic weapons that fire without warning? If WR-104's rotation axis has shifted even slightly toward Earth since our last measurements, would we know before the gamma rays arrive? How do you evacuate a planet? 10 cosmic threats, each one a reminder that Earth exists at the mercy of forces beyond our control or comprehension. These 10 events span 4.5 billion years of Earth's history, yet they share something that should trouble us deeply. Each one exists at the boundary of what our current models can predict or explain. The late heavy bombardment arrives precisely when life should have been impossible, yet life emerged. The Great Oxygenation Event kills nearly everything, yet creates the conditions for complex organisms. The Permian extinction eliminates 96% of all species through mechanisms we still debate. The Chicxulub impact triggers cascading effects that our climate models struggle to reproduce. Each catastrophe operates through feedback loops and planetary scale interactions that push our understanding to its breaking point. What emerges from this pattern is not reassurance about Earth's resilience, but recognition of how little we understand about the systems that govern planetary survival. Our models work beautifully for stable conditions, for gradual change, for the kind of universe where extinction events are rare statistical outliers. But these 10 events suggest we live in a universe where catastrophe is woven into the fundamental architecture of existence, where gamma ray bursts from rotating stars 25,000 light years away can strip atmospheric ozone in minutes, where volcanic eruptions can trigger ice ages that last millennia, where the magnetic field that protects all life can simply weaken and wander, leaving us exposed to cosmic radiation for thousands of years. The most unsettling realization is not that these events happened, but that they continue happening. Right now, WR 104 rotates in space, its axis unknown. The Yellowstone supervolcano builds pressure beneath our feet. The magnetic field weakens at an accelerating rate. Solar storms grow more intense as our technology becomes more vulnerable. We have built our entire civilization during the most geologically and astronomically quiet period in Earth's history, yet we treat this stability as permanent. These 10 catastrophes whisper the same message across deep time. The universe does not care about the continuity of life, consciousness, or civilization. The conditions that allow our existence are not guaranteed. They are borrowed time, measured against forces that operate on scales we can barely comprehend, following rules we have only begun to glimpse.